this lesson, we will look at the Doppler effect. There it is. You probably all heard it, and if you haven't, you just did there. What is it? It's the change in pitch of a sound. Did you notice that? Zzz, or whatever, where the pitch goes up or down, various degrees, and it's due to the relative motion, the relative velocity between the source and the observer. So, one or both could be moving, changing the pitch of the sound that's received. Does the speed of sound change if the source moves? No, because you know that the speed of sound depends only on the mediums itself. And even if the source is moving in the medium, it doesn't matter. The sound is still moving at the same speed. Let's consider a moving source. And to understand a moving source, first consider the source, which is this truck, maybe blowing the horn or just you hearing the engine, is not moving, and the distance between wave crests is highly exaggerated here, but the distance is lambda, and the frequency is f, and the time between crests is the period t. All right, that's 1 over frequency, and that would then be lambda over v, the wavelength over the velocity. So the speed of crests based only on the medium. We've got that down, and now let's consider the source moving. So now the source is moving, velocity of the source, namely that's the truck, it's moving in this direction. So in the time of the period of the oscillation, the time it takes to produce subsequent crests, the first crest has moved velocity times time. So this distance is velocity of the wave times the period. But in that same amount of time, the source has moved from here to here in that same amount of time. So it's basically chasing the crest. Distance of the source, Vs times t, because it's the same amount of time. So now the distance between crests has been foreshortened from this distance to this distance. What's that? That's big D minus this D, which is Vs times t. And that's the new wavelength, lambda prime. So there's lambda prime. So it's the original distance minus this distance of the source. Distance of the source, Vs times t. So we have lambda minus Vs times t. That's the new wavelength. And period is simply lambda over speed. And so now this can be factored out. The lambda factors out, so it's 1 minus Vs over v. The new frequency is, by definition, that same speed over the new wavelength. And of course, the wavelength is smaller, so the frequency is going to go up in this analysis. And it's the new wavelength, which is this quantity here. So we're going to put that in for lambda prime. But we also know that v over lambda, that is the definition of the original frequency. So we can sub that in for that equation and come up with the new frequency being the original frequency divided by 1 minus Vs over v. And you'll notice as the source gets larger, this quantity gets larger, the number in the denominator gets smaller, the frequency goes up. It's Doppler shifted upwards. If we do the analysis of the source moving away, we get a very similar result, namely the minus is replaced by a plus. And so as we increase the speed moving away, it basically lengthens the wavelength and the frequency goes down. So a quick example. We have a police car moving toward you at 50 meters per second, emitting a 600 hertz tone. What's the Doppler shifted frequency? So it's moving toward you at a very fast rate, 50 meters per second. So the source is 600 hertz. The new frequency, from the formula we just derived, is the original frequency over 1 minus Vs over V. So we can plug in the numbers. 600 was the original frequency. 1 minus 50, the speed, over the speed of sound in air, in meters per second, gives 703 hertz. Quite a bit different than the 600. Went from 600 to 703. That's very, very noticeable. Now think about what happens as the velocity of this source approaches to the velocity of sound. This approaches 1. 1 minus 1 then is 1 minus this is approaching 0. And the new frequency approaches infinity. Basically, the wave crests bunch up onto themselves, and they start piling on top of themselves as you reach the speed of sound. Let's now consider a moving observer instead of a moving source. So here we have a source sitting there, no motion. Distance between the crests is lambda. The moving wavefront at speed v. All right, so we have lambda between the crests moving at a constant velocity. And here it is. The source, the observer, moving into the crest. So basically what's going to happen is as the observer moves into the crest, it meets these crests quicker. So the crests are observed by the observer in less amount of time. In other words, the frequency, the number of crests per second increases, or the frequency increases. But it's a different way of increasing the frequency. Basically, the observer is punching into these crests. And the faster the observer moves, the more crests he or she meets in any given amount of time. So what's the relative velocity between the sound waves and the observer? In other words, what does the observer see? Well, as far as how fast those crests are coming at him or her. Well, the new velocity, the relative velocity in this case, is just the addition of the two. You're adding this velocity of the sound plus the velocity of the observer is how fast the observer sees these crests coming. Now the new frequency is speed over wavelength. It's the new speed though, and the new speed is v plus v0 over lambda. Lambda, v over f. So you could stick v over f in there. The frequency comes up to the numerator, and the new frequency is the original times 1 plus v0 over v. Looks quite a bit different than the other formula. It does look different. It has a similar effect, but it's a different effect. It operates differently in terms of what the new frequency approaches, for instance, when you approach the speed of sound. We'll look at that. Observer moving away, we have v minus v0 for the relative speed, and the new frequency is the original times 1 minus the ratio. So those are the two basic sets of Doppler shifted frequencies that you get from a source moving or an observer moving. Okay, so this time you are the one moving at 50 meters per second toward the police car. It's at rest, emitting that obnoxious 600 hertz tone. What frequency do you hear? Let's plug it into the equation. The original times 1 plus this ratio gives us 688 hertz. Notice that this is less than the 703 of the source moving at 50 meters per second. There's a good reason for that. If you think of these waves that are being produced, okay, and then the observer moving into the waves, it's hitting those crests quicker. But as we approach the speed of sound, with the observer moving at this, if the source is moving close to the speed of sound, those waves bunch up. And since they're right on top of each other and they're moving at the speed of sound, the frequency tends to approach infinity as the source approaches that speed. But if the observer approaches that speed, they're punching through the wave crests. And how fast would they have to go to approach infinity frequency? You guessed it, they'd have to approach infinite speed. So they never bunch up and converge on infinite frequency. In fact, as v0 approaches v, you're going to punch through twice as many in the same amount of time, because you and the speed of sound are both moving, well, at the speed of sound. And so you're experiencing twice as many crests, or twice the original frequency, which works in here. This is 1, 1 plus 1 is 2, twice the frequency. And now if the source and observer are both moving, we get this relationship without proof. All right, this isn't quite right. It should be v plus or minus v0 over v minus or plus v source. So put minus or plus here. Flip this around. The fonts aren't appreciated by Equation Editor, and I tried to fix it just now and I couldn't. So anyway, it makes sense because if you want to maximize this, if the shifted frequency is as much as it can be, it's a result of the original times the observer moving, okay, that increases it, and the source, if you put a minus sign here, v minus vs, then that makes the denominator smaller, and that's the way to get the biggest frequency, the highest frequency, and vice versa to make the smallest. Okay, so that's how that works. Plus or minus v0, minus or plus vs. And now, sonic booms and the shock waves that they produce. So if an object is moving in through the atmosphere, it's moving either at subsonic or supersonic speeds. If it's subsonic, then the Doppler effect is what we use to analyze it. But if it's supersonic, you produce shock waves. This can be illustrated initially by the simple graphics here. The source isn't moving, the wave emanates outward in all directions. An observer anywhere hears the unshifted frequency. Now, if the source is moving, you get this bunched up crests in the front, expanded in the back, bigger wavelength, smaller wavelength, higher frequency, lower frequency. All right, as long as the source is moving less than the speed of sound. But as it approaches the speed of sound, then you have these waves building up into a massive amount of energy, and you wouldn't even hear the thing until it's right on you, and then it would blast you with this huge energetic sound wave. Now, as you exceed the speed of sound, what you'll notice is we have basically tangent lines along these regions where the sound is radiating outward. It's a straight line that is across here. This is a shock wave, or a bow shock as it's called. An observer here hit by this will be hit with a massive amount of sound energy, enough to rattle the windows of your house, shake the bones of your body. I've been in that situation multiple times. It's really kind of cool, but it's also unnerving. If you've been to a airplane show, you may have experienced that. So I will intend to illustrate that in other ways as well. But that is a brief overview of Doppler and sonic booms.